welcome everybody. Good morning, good afternoon, good evening to everybody connected. The workshop motivator was basically a discussion at the SEG ML interest group between among people like Wei Chang Lee from Aramco, Bob, and me, that we were thinking, okay, SEG in particular is about exploration in geophysics and for hydrocarbon exploration, basically. But obviously, given the climate change and everything that it entails, we had to start discussing topics of transition, right? Transition to new energies. And specifically because this is data science conference, we decided to create this workshop where we discuss this transition, but from ML/AI perspective. And that's basically the theme, and that's why we have this great speakers, roster for today. So let's talk about the speakers. The first speaker will be Cécile Pereira. She has been with Total for some years now. Previously to that, she was with the Uranova as a project manager in biotech research, and she holds PhD and master degrees in computational biology from University of Paris-Saclay. Cécile, all yours.
Thank you. So let me just share my screen. Okay, so could you confirm that the screen is fine?
Yes.
And great. So hi everyone, I'm really happy to be here. So my name is Cécile Pereira, and I'm a researcher in machine learning, mostly applied to chemistry and materials. And today I will have a short presentation about end-to-end approaches to enhance the CO2 capture. So full disclosure here, since I'm not allowed to share unpublished work, it will be stuff that were done by our close collaborator during the year. And then I will just, to finish, show some main ideas of what we are working on. So to give a bit of context, since I'm the first one presenting today, as you may know, the carbon capture will be necessary to be able to reach the goals that we have in reducing the CO2 in the atmosphere. And globally, the goal is to capture 7.6 billion tons of CO2 per year by 2050. And here I put two graphs that are kind of constrained that we have currently. The first graph on the left, it's a CO2 concentration in the field feed streams compared to the minimum work in energy that we need in order to capture that CO2. And as you may think, is like higher is the concentration of CO2, easier is it to be able to capture it. So for example, SMR here, for stream methane reformer, it's around 40% of CO2, and that for the energy that we need to capture it, the minimum theoretical energy is not what we achieve yet, it's the minimum in theory that we could achieve. It's around here 2 kilojoule by mole of CO2. And so where we would like to go in the future, so there is some method that allow to capture CO2 with concentration higher than 10%. Where we would like to be in the future would be in NGCC, so for gas power station, and for direct air capture. And as you see here, direct air capture with a concentration of CO2 around 0.04%, it became really drastically difficult, and it will require a lot of energy to be able to capture that CO2 in theory. Now, if we look not anymore in the theory side, but in the real side of what is happening currently, if we look here on the second graph, you have for different concentration of CO2, the current cost of capturing that CO2. So what we can observe here is the biomass native biofuel. So for concentration of CO2 higher than 10%, The current cost is less than 100 euros by ton. That is kind of fine. And it's the goal that we would like to have for the other sources here. So for the natural gas combined cycle and for the direct air capture, where respectively we are currently more around 150 or up to 500-600. It will depend what you are looking exactly on the publications and the level of the technology on the readiness, but it's around 500 or 600 euros by tons. So that is far too much. And our goal with the project is to be able to reduce that cost to less than 100 euros by ton. So how we trying to do that? So we are working with metal organic frameworks. So what is a metal organic framework? It's composed by metal cluster, an organic linker, and when you have those metal clusters and organic linkers, they form a materials, and that is a 3D porous framework. And then you can blow some stream into that framework and try to capture the CO2. And here, what I'm trying to show with the part here on the left is that there is a large number of metal clusters that are possible, and you can combine those metal clusters with a lot of different organic linker, and those combinations you will end up with completely different porous properties. And if you look into the literature, there is more than 6,000 cataloged architectures of MOF. And there is a very huge number of hypothetical MOF that never synthesized because you can kind of play around. And so the idea here is like with this huge spectrum of solids, how can we identify an optimal adsorbent and its optimal process? So what we would like to have is the best material put in the best condition in order to be able to capture the CO2. To do so, since it's a machine learning discussion, what we could apply for the CO2 capture, we could work with a predictive model, trying from a metal organic framework to be able to predict some properties. So it's the first line here. We can also work on generative model with the idea of being able from a lot of hypothetical MOF that we currently have to propose new MOFs that might have some properties of interest. And we can also work on the optimization of the process, meaning for one given MOF, what would be the best process I should work with in order to achieve the best capture possible. So today I will not really discuss about the first one, that is the most classical one. I will try to go about with the two last one, the generative models and the optimization. So let's talk about generative model. For the generative model, this year, Tom Wu and collaborator had a fairly nice publication. And it was fairly nice because it was something that was already out there that they adapted to MOF. So they worked with VAE, so variational autoencoders, and they applied that to specifically to the MOF. So how do they did it? They work with the ages. Okay, so remember a metal node and an edge and then a topology. So they work with the age and use them represented as a graph. And then they use the vertex, so the nodes, and the topology as classes. So there is the number is finite. From those, they use the approach in a semi-supervised way. So they had those information for all the full complete database with several thousand hundred MOF. But also for some of them, they had additional information, and that additional information was properties on the way the MOF was capturing the CO2. So for the encoder, they had one part for the graph part and one part for the classes. They create the latent space, and for the decoder, so the VAE, the principle is normally fairly classical. So you are trying to compress the information in the first part, and then you decode that information, trying to obtain this identical information that you had at the beginning. So you try to be able to predict the same thing with a fewer number of variables. So here for the decoder, they decode for the age they decode for the vertex information and also for the properties. By doing so, they create a latent space that is biased in function of those properties. So you will be able to go through the latent space in order to kind of modify, inverse, it's a way to do inverse design, your MOF in order to meet the properties of interest. That here is an example of what is happening if you are applying that method on starting from MOF5 in the latent space. So MOF5 is a fairly used MOF for the capture of CO2. So it's here on the left. It has a CO2 uptake of 2.8 and CO2 against CH4 selectivity of 2.2. The goal here is to increase those two values. So if moving into the latent space, we can go from a CO2 uptake and CO2 CH4 selectivity of the MOF5 up to here going having something that is 3 times higher for the CO2 uptake, and the CO2 CH4 selectivity, it's 10 points ahead. And what we can observe is that we are going from a really fairly simple linker, and we can observe different kind of linker and different kind of topology, because we are moving not toward similar topology, but toward those properties. So once we get a good MOF, we need also to be able to put it in a good situation, like the good process to be able to have the best CO2 capture. And that is the work that Arvind Rajendran team is working on. So for the processes, you can have several steps possible. The first one is the pressurization. So here it's closed and you will add pressure here. So you will have your stream here. You can have feed, just it's open both sides and you push here through the feed through. You can blow down, so you can here have the column closed and decreasing the pressure. You can have one high pressure on the right, one small pressure on one high pressure on the left, sorry, and a small pressure on the right, and having so moving through from left to right, and you can have a purge. And you can think about way of combining that a lot of different ways, and there is a priori no real good reason to take one instead of the other. So what Arvind Rajendran team looked at is for the same material, the same starting point, same material, they are trying several combination and also several parameters for those processes. So because the pressure here, you can define that you go up to a certain level, and that level will be one of the parameters. Okay. So doing so, for the same material, you can observe that. So here on the graph, you have one curve by process. Then you observe CO2 purity against CO2 recovery, and the goal is to be here on the top right. So what we see is that for the same material, you can have a really huge difference in function of the process that you are applying. And it's not because your process is really complicated, like here in pink, that you will have, or here in yellow, that you will have a really high value. For example, the yellow here is fairly bad compared to the other, and the pink one is fairly good. So here the question is, so then the question is, once I have the best material, I also need to put it in the best situation. And to do so, Arvind Rajendran team did a machine learning approach where they take into account the material features and the process features. So for one given process, they are trying to obtain the best result possible that could be achieved by this process. And to do so, they apply a machine learning model that is called MAPL, that is a deep neural network that that you are applying instead of performing a simulation, and that is able to give you the result of the practical limit for that simulation. In order to go through all the parameters and all the materials, they are going applying a genetic algorithm to explore the space. So here the goal is to look at the energy, best process operation, and to obtain the energy for the best adsorbent and the productivity for the best adsorbent, and to be able to then to select the best process if we had the best condition. So we went through predictive models, generative models, and optimization. Let me just sum up. At TotalEnergies, we are working with both the University of Alberta and the University of Ottawa on the methods that they discussed. So starting from what they have published before, now we are building on top of it. And that is the main idea of the project. So it's a 4-year project, and we are working on first a high throughput pre-screening, including the VAE to propose inverse design sum-off. We are working also on the process screening with Arvin Rajenram work. We have a part that I didn't discuss it here, work on molecular modeling for CO2, so for water stability, because water can have a huge impact on the quality of the material. And once all of those numerical steps are done, we will be able to synthesize and to do some lab scale demo. As you observe, we will have loops here that allow us to take into account the result of one step to kind of improve the step that was before. Our goal is in 4 years to be able to have a laboratory pilot and to be able to propose some carbon capture for NGCC and direct air capture. I would like to thank the team I'm working with, so people from TotalEnergies, and in particular Fracking, that is the project manager on the topic. I am in charge of discussing the AI, so the machine learning part of those projects with Arvin and Tom, and a special thanks to them and to the postdocs that are working on those projects. Thank you. It's all for me, and I can take questions.
So the floor is open for questions. You can either do it directly or on the chat. I have one question. So basically the material we're talking about here is absorbent for air capturing only, or there's other purpose?
So it's an adsorbent, and it could be used for direct air capture or for capture of CO2 in whatever condition, but it was also used in, so modifier also used in a lot of different other ways. For example, for H2, there is some application for H2 or O2 storage. So it's could be applied, it's porous material, you can see it as a sponge, where you can go put some pressure on it, add some materials, and release it when you like to. And here, what we discussed is one way in particular to release it, that is pressure. But you can also think about temperature swing, for example.
So that's a combination of the absorbent, the material, and the process, basically.
Exactly. So you need to have a good material that is able to take this, to capture the CO2, and that have a high selectivity compared to the other component. But you need also to be able to release it fairly easily, because it's when you are trying to release it that you will need a lot of energy. And what we want to is to have something that have a small cost, so that the selectivity change fairly quickly when you need to release it.
There's like what was the metric for absorbency? There's like a metric that you are using to drive the progress?
Yeah, so what we are going for, it's so it's just here. We are going for the energy consumption and the mole of CO2 capture by unit of volume for the adsorbent at the scale of the process. At the scale of the material, we will go for the selectivity between the CO2 and the other compounds that are in the feed.
Do you have an estimation of the PR right now for the material? I mean, what would be the good number to achieve, and when, right? Because these things are, time related. To 250, we had to be capturing a lot.
Yeah. So we already have some methods that are capturing. What we are trying to do is really reduce the cost. And I think here the the real question will be be able to synthesize the MOF, because those are things that we can dream about. There is a lot of discussion about those MOF, but they are fairly difficult to synthesize. So I would say that having the best hypothetical MOF, it would be, I think, fairly easy to do. There is several, like the VAE approach is already giving fairly good results. What will become difficult will be when we will try to have it in real, in a large quantity for a price that will not be too expensive. That will be a bottleneck, I think.
So most of the changes are going to happen on the process side in terms of cost reduction.
So having a MOF, that we need to think about a MOF that we will be able to propose and that will be able to be synthesized. So we might at one point go for something that is not as efficient, but that is easier to do. Because we need to produce it in a very large quantity. So currently we are at the step where we are thinking what would be the best combination between a MOF and a process. And next step after it, and at that scale, we will have maybe 100 of potential MOF. And then the second step that I think will be more difficult will be to be able to know among them which one we want to synthesize and how to make them. But it's maybe biased because it's not what I'm doing. So
any other questions from the floor before we send Cécile, Cécile off and thank for her? No? Well, Cécile, thank you very much for helping us. I know it's late in Paris, but we appreciate you are staying with us, and I guess you're going to stay around a little bit longer, right? In case people have questions on the chat. Thank you very much. And now we move to the second talk. It's going to be given by Heiwei Tang. Heiwei is a postdoctoral staff member at Lawrence Livermore National Lab at the Atmospheric, Earth, and Energy Division. She holds a petroleum engineering PhD from Texas A&M. And she's also serving as an associate editor at the Journal Petroleum Science and Engineering at the SPE organization. So, Heiwei, the floor is yours. You can go ahead. Thank you.
She says in the chat that she needs to rejoin.
Ah, just. Okay, let's give her 1 minute. Something about the audio, yeah, happens.
So just in the meantime, I'm not sure we'll be able to stay here very long. So I shared my email address on the mail on the discussion. If you need to,
sure,
if you have any questions,
you can share that on the chat. So if people want to ask you questions and how to collaborate in the future or things like that, yes, absolutely.
Thank you.
Hi.
Hello.
Here's Heiwei. I just rejoined. Can you hear me well?
Yes, I can hear you well. So
okay, great.
You can go ahead. I already introduced you in case you missed that part.
Okay. So you can now see my screen.
I can see your screen, but not in presentation mode. Okay, now it is.
Okay, great. So should I go ahead start?
Yes, please.
Okay, thank you. Hello, everybody. Here is Heiwei Tang and from Lawrence Livermore National Lab. Thank you for attending this meeting. Today I will introduce a deep learning accelerated data assimilation and forecasting workflow for commercial scale geologic carbon storage. Okay, 40% of global CO2 emissions come from industry, Well, 90% of these emissions can be prevented from reaching the atmosphere by geologic carbon storage. For a commercial scale GCS project, we usually inject millions of tons CO2 per year. There is a strong need to reduce the cost of this project by using rapid decision-making methods in reservoir management. So the goal of this research is to build a fast and automated data assimilation and reservoir performance forecasting workflow for data assimilation. Here I present a typical data assimilation workflow. So started from initial reservoir models, we can predict pressure and saturation from a high fidelity forward model. Then we can compare it with observation data. If they match with each other well, then we will do performance forecasting. If not, we will go through an inverse model engine to update our gases of reservoir models. In this workflow, the high fidelity forward model is the most computational expensive component. Therefore, we propose to replace it with a deep learning based surrogate model to speed up the whole data assimilation workflow. So our target application scenario is the commercial scale CO2 storage project. Here we build our reference reservoir model based on a classic shelf depositional environment. And we consider 4 injectors honor a total injection target of 2 million metric tons per year. Well, we also show the reservoir simulation results from CMG. It will serve as our synthetic observation data. So we consider the seismic inverse, the CO2 plumes, as our observation data, as well as the pressure from monitoring wells. For the seismic inverse, the CO2 plumes, since the reservoir depth is much larger than the reservoir thickness, so it's actually impractical to really resolve the vertical details of these CO2 plumes. Therefore, in generating our synthetic data, we first apply a 10% threshold represented by this purple contour. And then we will project these 3D contours onto a 2D plan view plane and to form our final observed CO2 plumes as a binary field. Here, we suppose that we are dealing with a real GCS field, which means that we are in general lack of well data to constrain our initial gases of reservoir models. Considering this flat structure reservoir and the 2D observation data, we hypothesize that a 2.5D reservoir model or a single layer 3D reservoir model is likely to be adequate. So we intend to form a closed loop data assimilation and forecasting workflow, where the adequacy of the underlying model will be evaluated against the utility objectives of the workflow instead of against the ground truth reservoir model. Following the above design logic, here is our whole data assimilation workflow, and I will introduce several essential components of it. The first is to generate initial gases of reservoir model to mimic the true permeability field. We just using our in-house fractal geostatistical model to generate some unconditional Gaussian fields. And we want to guarantee that the features of the generated fields to be rich enough so that the constructed response space can match with observations. Here, the major challenge is that we need to bridge between the saturation prediction and the full 3D model and the 2.5D model. For example, if we use the vertically mean porosity and mean permeability to do a 2.5D simulation, as CO2 plume will be like this, while the true observed plume will be like this. The difference is because that in the full 3D simulation, we have different CO2 plume shapes and at different depths. Well, for the 2.5D model, we basically assume a same CO2 plume shape all over the reservoir depths. So in order to match with the observation data, we need to introduce an additional history matching parameter. We named it as porosity scale factor, and it can help scale the porosity down and to in order to match the size of the CO2 plume. Here we can actually calculate its true value based on its physical meaning. So it can be calculated by the ratio of the 3D, the volume of full 3D simulation and the volume of the cylinder formed by the 2D plume. And another important part of this data assimilation workflow is the deep learning surrogate models. Here we want to replace the high fidelity forward model with deep learning based surrogate models. And we generate two surrogate models, one for saturation and one for pressure prediction at the monitoring well location. So for the pressure prediction, we use a wet residual net structure, and the input is the permeability field, and a map indicates time. So our output will be the pressure at each monitoring well. And for the saturation prediction, we use a residual U-net structure, and this structure was first proposed by Dr. Dolovsky's group for subsurface for the subsurface prediction. And the basic idea is to see the reservoir simulation problem as a map-to-map regression problem. And here we show how we can predict for a single well injection scenario, and we can get good results. Well, if we directly use this network structure for multi-well injection scenario, then the predictions will not be really good. It seems that the network cannot really figure out where the plume should be and how large its size should be. So the major difficulties is that the 4 wells are following a total injection rate target, which means that the injection rate to each well is different over the time. So the network struggle. That's why we decide to separate this challenge task into 2. And for the first step, we want to predict an injection allocation ratio for these 4 wells based on the permeability map. And this can be achieved by the ResNet structure. And then we use this value scaled by time and porosity scale factor. The final value indicates how large the plume size will be. And then combined with permeability map as input, we will have our final saturation CO2 plume prediction. So here we used simulator to generate training data, and we consider more than 10,000 permeability maps. And GeoSAX was run for 10 years, and with pressure and saturation recorded at each year. Here we evaluated 4 different sizes of the training permeability map on model accuracy. So the metrics to be considered are RMSE, R-square, and SSIM. We can see that basically the pressure model is more sensitive to the number of training maps, and we need a relative large training maps, basically larger than 5,000, to get a good result. Well, like little training maps to get a good result. Here we evaluate model based on the testing data set. We randomly selected several testing data from the testing data set, and we ranked them in the order of increasing porosity scale factor. So we can first see that both models give good predictions based on the testing data. And also, as porosity scale factor increasing, the CO2 plume size decrease from a really large plume shape to several pixels around the valve. And then we also test the model capability to interpolate within the training time domain, as well as to extrapolate outside the time domain. So our training data is recorded each year within 10 years. Our model not only have a good interpolation capability within the 10 year, but it can also give reasonable predictions at 15 years and 20 years. So we use, finally, with all these parts being assembled, we apply an ensemble-based method called ESMDA for uncertainty quantification. Here we use 4 ESMDA iterations and 10,000 ESMD ensembles, since we considering a much larger uncertainties. And here I show the ESMD results iteration by iteration. At the first iteration, we can see our prior mean and standard deviation is unconditional field. So it's basically a constant number with no bias of saturation plume prediction. And here is our pressure prediction and also porosity scale factor both have large uncertainty range. And then after the first iteration, the porosity scale factor decreased a lot to match the observed plume size. And then the second iteration, the plume shapes are matched much better. And then for the third, they have pressure matched really well. The fourth iteration, the results are similar to the third iteration, and we basically get the convergence result. So I want to summarize the computational cost of this workflow. If this workflow is conducted based on a physical simulator like GeoSAX, it will need more than 10,000 core hours to run, while the current model can run like within 2 hours on my own MacBook or within 1 hour on a workstation. So to summarize this work, we developed a history matching workflow for closed loop prediction by assimilating saturation plume data and pressure data. And we developed a deep learning-based surrogate model for multi-well injection scenario to significantly reduce the computational cost of the workflow. And since actually in this workflow, I only introduced 2 parts of it, and I didn't go into details into how the parameterizations are done and how I reduce the data space dimension. So if you are interested in it, you are welcome to see our recently accepted paper on International Journal of Greenhouse Gas Control. And that's all of it. Thank you.
Thank you very much, Heiwei. Very interesting presentation. So the floor is open for questions. No questions? People are eating their lunch, maybe. So maybe I will have, can you go back on the slides a little bit? So we have some conversations on the slides. I was thinking first that, you know, the government, when accepts carbon sequestration projects, they ask for forecasts that are in hundreds of years, right? Do you think you
Yes,
can
yes.
extend the forecast to something of that level, including the uncertainty quantification?
Based on this workflow, I think it has the capability to predict even longer time frame. And since it's also mainly a demonstration of concept, so we only forecasting to 10 years. But as more data come in, say if we can have 10-year data come in, then we have more confidence to predict for 20 years, 30 years, or even 100 years. But yes, it's definitely possible.
Okay. There's a question on the chat. How many simulations were required to develop the deep learning model? Is it 2 hours or 2 hours only for the deep learning model runs?
Yeah,
I guess it's
here,
about this slide, right? Yeah.
Yeah, here I have the computational cost summarized. So so remember that we have a porosity scale factor. Actually, it means that I need to run 2 separate simulations for saturation and pressure with different porosity. So for each single run, it takes like 10 core minutes. It's not that bad since it's actually 211 times 211 field. Not super large, and GeoSex is really good at computational efficiency. Hope that answered the question.
Yes, to a certain extent. Okay, he has a follow-up related to the 13,000 hours.
Isn't it the 3,000 core hours she has listed on the slide? Isn't that the answer to his question?
Yeah, so this is calculated based on the whole data assimilation workflow. Since it means I have 10,000 ensemble and I have 4 ESMDA iteration. So the forward simulation need to be done like 80,000 times. And that's how this number.
Yeah, but to only build the deep learning part, as Bob mentioned, basically you have the answer there, is this 3,000 course hours, right?
Oh, yes.
That was the only, the actual training cost, we're saying.
Yes, exactly.
Right, and the 13,000 hours is an estimate, right? In case you do that with the full simulator, right?
Yes, it's an estimate. I didn't really do it.
Yeah, but you don't have problem with that. I mean, Lawrence Livermore have big computers, right?
Yeah, but we have a lot of supercomputers, but it's kind of silly to do this 13,000 hour simulation if I have the surrogate models.
So what's next for this project? Are these surrogate machine learning based approach being incorporated in the standard workflows, or how you see the next steps for this?
Okay, great question. So here we can see our model setup. Here we only consider like 3D seismic data and pressure from monitoring well. And since we also have good geomechanics simulation capabilities, so we actually want to assimilate INSAR data as well. INSAR data basically give us a measurement of surface displacement, and it's strongly correlated with pressure, like the pressure map, the pressure in the reservoir. So we are working on this, and also for this from the deep learning part, we are currently, although we call it's a 2.5D simulation, but it's basically a 2D simulation. So we also extend.
I don't think you're doing native 3D convolutions. Then your laptop will not be able to do that, I tell you.
Yeah, so we actually extend it to full 3D deep learning surrogate models. Yeah, and it's this part actually has already been done. Yeah, and since this work is funded by DOE Smart Initiative here, and so we are just concluded our phase 1, and phase 2 will start next year. We will have field data coming in, then it will be more interesting.
Okay, Sounds good. Let's have it next year with the field data.
Yeah.
Thank you very much, Wei.
Yeah.
Thank you for coming and showing this interesting approach. Now it's time for Bob. Bob Clapp is the technical director of the Stanford Center for Computational Earth and Environmental Science. He has been at Stanford for many, many years, including his, educational part. So in total, it's like 20 years. Next thing, he will put a statue of himself there. Basically, his work is around geophysics algorithms and HPC, and he's an expert on these topics. And yes, Bob, I think that's good enough as an introduction. You got to go.
Okay, so kind of I'm fitting in sort of a different piece than the previous two speakers, and I'll sort of give sort of where that all fits in a minute. So basically, I'm going to be talking about microseismic event detection for CO2 sequestration. And I didn't do most of this work. Most of this work was done by Fantine, Page, Ariel, and Ben, who are all at Stanford, or Ariel's now in Israel, but they were all at Stanford when this work was done. So I'm going to kind of give you a bigger picture. So you heard on the first talk how much CO2 per year we think we can get by 2050. We really need to, basically to stay within the 2C limit, we need to somehow get rid of 800 to 1200 gigatons of CO2. And trees aren't going to solve the problem because that's basically a temporary sink for CO2. Fires and just the tree dying and decomposing basically returns almost all of that to the atmosphere. So what that means is we're going to need thousands to tens of thousands of sequestration sites throughout the world in the next few decades. So kind of one of the things that's sort of, again, putting this in perspective, the way a sequestration site is found is you're basically looking for an area where you have a bunch of geology and geophysics information. You're going to start there. From those sites, you're looking for, when we're talking about saline aquifers, we're looking for something that can store a bunch of CO2. And then what's really important is you're looking for to make sure it won't leak. So that means you need what's called a cap rock. You basically need a seal that prevents the CO2 from moving up. And then it's what you just saw. Once you've got kind of this site chosen, you're going to need to do an injection simulation. So what that's basically what you saw in the last talk. You're going to need to go and figure out what's going to happen as you inject CO2 for the next 10, 20, 30 years. How is it going to move around? And you're going to be talking to a regulator. In the US, that's going to be the EPA, or more likely a state regulator. And they're going to set the rules. And basically what they're going to say is, you need to tell me where that CO2 plume is going to go over time and how you're going to make sure you know where it is. And if you're wrong, you're going to have to do either shut down or do something quite expensive to figure out what's going on. So this is an example of sort of what you don't want to happen. This is kind of an example of CO2. You've injected it in this well, and you can see it leaks through a fault. So that's what we're, one of the scenarios that we're trying to avoid. So what's really going to be important is monitoring this. And there's going to be, how you monitor is going to be really site specific. But one of the things that's going to be really likely to happen is you're going to need to install DAS in wells. So DAS is kind of a cool thing. You can imagine a fiber that carries the internet. Well, that fiber cable has impurities. And you're going to, if you sort of hook up a laser to it, you can kind of look at how the backscatters of those impurities and how they change basically can give you a seismic response. It can give you a lot of other stuff, but that's kind of the one for in this case. And why that's important is the little faults or little kind of microfractures that cause potentially the leak that you're seeing on the left are something you can actually pick up and see and map, and you can kind of see what's really going on. Okay, so the first problem on this is these interrogators can produce terabytes per day. So this is going to be a computing on the edge problem. This is, you're really going to want an ML algorithm that can go in and figure out what in all of this data is actually important. Now, the issue is right now there are currently very few active CO2 sites and even fewer with DAS in the well. So kind of to test this methodology, what we did is we found a corollary, a fracking site. And so that in that case, you're actually creating these microfractures. And so here's kind of an example of the site we got data from. The blue and the green are places where you're going to let off little explosions under the ground and create microfractures. The red, this line in the middle, has this DAS where we're going to actually be measuring and looking to see if we can find those fractures. So now, as I said, I didn't do most of the work. And one of the things I was very glad not to do is we had a couple people picking events. So you can imagine each one of these little explosion happens, and that's called a fracking event. And you wait 2 hours or 3 hours, and then you do another one. So we had a couple people pick 7,000 different events that they saw, microfractures that they saw happen. And then we found another set of 10,000 different events where we thought it was all noise. Kind of give you an idea what these look like. This is an example for people that haven't seen seismic data. What you see as coherent, this hyperbola here, this is what we consider, this is a kind of an example of a microfracture. And we can have different type of arrivals. These can look a lot different. So kind of, they can be, this is an example of a smaller one. So you're seeing it looks less coherent. And, these can have kind of different behaviors depending on what type of rocks and what's going on sort of in the geology around the well. So these are all kind of examples. So so for 2 of these fracking events, they picked 7,000 events, tons of noise. So then what we're going to do is start kind of feeding our network. Now, when you handpick these, you were really careful, and you picked, you probably clicked on the center of the hyperbola. But as we're kind of spanning through all this data where we don't pick, we're going to need to handle all the cases where, it can deal with the center of the patch doesn't represent the center of the event. So we're going to kind of augment the data by kind of moving around our patches around our known events. So basically, now we have a bunch of data. It's time to actually do a network. And this is a kind of a package that Fantine has, which is doing hyperparameter tuning. So this is kind of an ML group, but just to kind of give you a little bit of background, what this means is when you're making a network, you're making lots of decisions. The number of filters, the size of the filters, the number of layers. Basically, all of these are parameters that you could manipulate to get kind of the ideal network. This hyperparameter tuning is basically searching in a smart way through this parameter set. And the advantage is you can end up with a network that is smaller. Networks that are smaller tend to have advantages. There's less issue with overtraining. They're going to be generally turn out to work much better. So we did this, and let's kind of look at the results in a lot of different ways. So this is one of the handpicked stages, and what you're seeing here is these horizontal lines each represent time, and the bigger the circle, the more the events picked at a given time. Now we can also go and look at the result of the network, and you can see it looks similar, but it looks more continuous. And this is just an issue of discrete versus continuous, because we're going through a time series, a series of patches. We're going to kind of see these events show up many more times in many more patches than what one event will be picked in many different patches by the network. But it looked quite good. Now this is kind of what we picked versus what the network saw. And if we kind of instead look at what it saw on an event or a series of events we didn't pick, it seems to pick a similar pattern. We can kind of look at, there were 30 stages. We can go and look at the total number of events as a function of time after this initial, like a little explosion has happened. And they look fairly similar. So they look like it's doing the right thing. So that's all nice and interesting, but kind of let's go see what it actually did. So we can also go and figure out the locations of these events. And I'm going to talk about how, but it's kind of cool. We can go and see that exactly what we don't want to happen in the CO2 case is happening in this fracking case. We are basically creating fractures that are moving away, and we're basically creating pathways for fluid to flow. So, but what it kind of shows us is this pipeline allows us to get what we want, which is the ability to find microfractures, find their location, and kind of detect what's going on for the CO2 case, kind of that reservoir. So, looking at it another way, here's our positives versus negatives, our probability distribution, and this is exactly the type of thing we want to see. The network is pretty sure. When it thinks it's a positive, it's very sure it's a positive. When it thinks it's a negative, it's pretty sure it's a negative. Now we can kind of go look at what it saw. This is an example of one of its false positives. So we had gone and marked this data set as not having any coherent events, but if we but the network thought that it was an event. If we kind of do some processing, kind of take the envelope in here, we can see that there is an event that's beyond humans' ability to really see. And that was kind of the cool thing. We went through and we basically went through all of our false positives, and every one of them, we came to the conclusion it was just something we missed. So this network proved to be more effective than a human. So kind of another way it's kind of fun to look what the network is actually doing is we can look at an example and look at the activation. So what you're seeing here is here's an event that's kind of somewhat seeable by the human, and we can kind of look at all the different filter banks basically, and you can kind of see as we go through it, it definitely is kind of activating, and it's really, you can see kind of where it sees and detects that something going on. And we can do that same thing with noise. And if we look at the noise, this is kind of a noise event. And if we look at the activations here, it's all pretty dang random. So the network is behaving the way we would want it to behave. Now, kind of another fun thing we can think to do is break this up into clusters. So instead, now we have all of these events that we say are real. Let's see what kind of, if we can categorize them and sort of break them up automatically and learn something. So here's an example of one cluster and another cluster. And kind of, if we just look at these two, you can see that this cluster 3 has some linear events that we're really not seeing in cluster 1. And this is actually basically backscatter against fractures. So what we have basically come up with a scheme that is automatically finding examples of where we have fractured rock. So you can think this is going to be this kind of automatic processing, automatically being able to detect important and categorize different events is going to be something that's going to be key when you're doing CO2 monitoring. Okay, you know, there's lots of, we could go through all the geology, but I know we're almost out of time. So basically, these different clusters represent different geology and different, different statuses the reservoir is in. So, sort of some conclusions. The network is able to detect events better than a human. What we're doing right now is we are currently running this algorithm away from the time where we actually had these little explosions, and it's actually still working really well. And this is becoming even a closer corollary to what's going to be happening in the CO2 case, but can't show that data. Basically, getting permission to show it takes too long. And what's really cool is we're going to start getting data coming from some CO2 sites this spring and running this exact same approach on it. And I'll stop right there.
Thank you very much, Bob. We have time for at least maybe one question. Does everybody on the chat have questions for Bob? I have a question. When you said time away, you mean forecasting?
No, we're going to basically, this interrogator was turned on for a week before any attempt to kind of frack the reservoir. So this is basically just sort of the background microfractures that are happening as you are pumping. So it's almost exactly the case of what you're going to see when, instead of pumping in, pumping in, which we're going to be doing in CO2 sequestration, it's pumping out. But there was some pumping in of water. So it's really, really close to exactly the case that we're going to see with CO2 injection.
Okay. Well, we are out of time, and this time I will just to acknowledge everybody that was facilitator for this to happen. So thank you very much to the organizers, Mackenzie and Melissa, and nice people at Kennedy Institute and Rice University as well. Thank you very much for attending, and